So, first of all, the assignment that I mentioned on Tuesday is posted on Connect. The assignment is due February 25. So, it's not much work. The instructions are there. It's 1 or 2 hours at the most of work. Okay. So now let's continue. We're starting today the second segment of the course, which is interfacing. How to connect the sensor to the rest of the servo system. So it sounds like a very mundane and irrelevant topic, but actually there is a lot of tricks and there is a lot to know. How to connect a sensor, especially a sensor which is a sensitive sensor, a low-level output sensor, how to connect it to the amplifier which is driving the servo actuators. So there's a few things to consider. So if we have a sensor, okay, and we have a wire or a double wire if it's differential. Now we're connecting it to the box, which is a controller. And the controller can be as simple as just an op-amp, or can be something as complicated as complex software which implements a servo. Now from here you have the actuator. And of course, being a servo, you have some kind of a feedback loop, not necessarily electrical, because if the actuator moves something, the sensor is monitoring how much it moves. So the connection can be optical, can be magnetic, it can be whichever way the sensor works. Okay, so this is not necessarily a wire. Now, there is a couple of common elements that I mentioned that if you do just that, you are very susceptible to noise and to aliasing, which we'll discuss separately. So I mentioned already that it's a good idea to insert a filter, okay? And this filter can be a low-pass filter or a band-pass filter, depending whether it's AC or whether it's a baseband, meaning DC coupled. Okay, now sometimes it's also advantageous to put a filter here, okay, and we'll discuss in a moment why. So this also could be another filter, okay. And there is a whole bunch of other issues of grounding, shielding, interconnect, how to actually do this connection. Because if you're getting any kind of electrical coupling from these wires to these wires, then you have some uncontrolled feedback that can cause oscillations, and also you can have noise. There could be noise picked up on the wires, but there could also be coupling that you are not interested in between the wires. So certainly it would be a bad idea to run these 4 wires together, because there'll be, okay, so there'll be also spurious coupling, okay. Sometimes this is referred to as crosstalk. Okay. Coupling. The crosstalk is a term taken from telephony or telegraph, because in telegraphs and telephony, when you had adjacent lines, you could hear a conversation on another line, just because the lines were coupled inductively and capacitively. So the word crosstalk is a very old-fashioned term, but sometimes it's referred to. Okay, so the first question, let's just cover a few basic questions. Where is it better to put the filter? Is it better to put the filter at this end of the cable or at this end of the cable? What do you think?
Close to the controller.
Pardon?
Close to the controller.
Close to the controller. And why is that?
Because it can filter the noise from...
Yeah, because if you put it here, after the filter, it still can pick up noise. So obviously the filter has to be as close to the amplifier, so it filters out the noise as well. Okay, now, why do we need a filter on the output here? Because this is high level. Typically this can be low level, but this is always high level because it drives an actuator, a motor, a stepper. So why do we need a filter here? Any thought? Imagine that this actuator is maybe a few meters away. Sometimes the controller is at one place, but the actuator can be at the other end of the room or at the other end of a machine. So why do we need a filter here? The actuator is not sensitive to noise. It's high level. Yes?
Because you set it a modulated signal?
Very good. Because it can radiate noise, and because most things today, they work with a PWM. Like when you look at a solenoid or a motor today or a power supply, in the old days it was true variable current, variable voltage. Now today almost everything works by pulse modulation in order to save cost in the device. So if you look today at a stepper motor driver, like a micro stepper driver, if you look at what's called a variable frequency drive, like these big things which can change the speed of motors, they don't output a variable amplitude. They all output PWM, which means pulse width modulation. So when they want to make a sine wave, they don't actually output a sine wave. They output pulses where the average is a sine wave. So almost everything you look today, power supplies are switching inside, switching power supplies, motor drives, like the ones you buy to change speed of motors. If you put a scope on them, what comes out is pulses. Okay, basically everything is done with pulses because this way it's cheaper. So because of that, especially because it's high level, there are pulses here which radiate like crazy. Okay, why does a pulse radiate so much more than a sine wave of the same value? So this is pulse, equivalent is a sine wave, but why does the pulse radiate much more than the sine wave, which is identical to it?
The frequency is higher?
Of course, because this, if it was really totally vertical, this would be an infinite spectrum. Okay, and that's very bad. If you open any switching power supply, like a switching power supply on your PC, okay, there's lots of filters here. After the pulses, there's lots of filters because the fear is that this is a terrible waveform. It has all frequencies in it. Okay, so if this is not right next to the controller and you can shield it well, you always have to put a filter to cut out the noise from a switching device. Okay, so we have a filter here. Next question. Typically we put an amplifier after the sensor to amplify the signal. Where should we put the amplifier? At this end of the cable or at this end of the cable? At the sensor end or at the controller end? And why is that? That's correct.
So you don't want to amplify the noise or any deviations that are...
Very good. Okay. So if there is an amplifier, it always comes at the sensor end because you want to set the highest level signal possible on the wires. Okay? Good. Okay, so that's the general layout. So now we're getting to the question which looks mundane, but it's not trivial at all. If these are farther apart, let's say it's a few meters apart, which happens a lot, right? I mean, which kind of wire should we use? We already learned before that it's good if we can make it differential. It's sometimes very good if we can make it AC coupled. But physically, what should we use? Which wire should we use? Because that has actually a very large effect on the performance of the system, and that's a part that I find students most ignorant about. So I'll just pass along here the most common types of wires. Okay, one is just a regular wire, like an electrical cord, straight wire. The other one is what's called a twisted pair. Twisted pair is just two wires twisted together. Okay, the third one is a shielded wire, like an audio wire or a video wire. If you look at your headset or anything with audio, it usually runs on a shielded wire, okay, microphone cable. The fourth one is a multi-conductor shielded cable. Okay, you have a few conductors with a shield. You can see it at the other end. And the fifth one is a coaxial cable. Okay, so all of you have used all of them, but I want to go over it and explain what the differences are. So just pass it along so people don't fall asleep, they have something to do. Okay, and so let's start with a straight wire, like an electrical cord, or the same wire, which is a twisted pair, two wires twisted together. Which one is better to connect a sensor to a controller? twisted. And why is that?
They'll counteract each other.
Pardon?
They won't couple.
Why wouldn't they couple?
Isn't the windings?
No, okay. Okay, so that's a surprising thing that I noticed this in previous years, that none of the students, although you use this all the time, none of the students actually understand which wire to use where. Okay, and that's very critical. Okay, so yes?
I think we're trying to minimize the area so that like there's no changing magnetic flux and eddy currents.
Changing the area between the wires?
So that's why we twist them.
No, okay, so you are right about we are trying to bring the wires closer together because the wires form a loop, basically. You can say the area, if there is a magnetic field here, the wire which is connected to this amplifier forms a loop, and you want to make this loop as small as possible, right? But the twisted pair and the straight wire have the same loop area. Like the wires are as close as possible in both cases. What limits their distance is the insulation. So in both cases there's the same loop. Okay? Yes?
Does it matter for a sensor to the amplifier what type you use?
Very critical. It's critical. Like the difference in a noisy environment, this would not work and this would work. Okay. So it's as critical as that. And if you take apart anything which is designed to work at RF, at high frequency, where the coupling problems and crosstalk problems are worse, you never see this in a high frequency device. If you open it, either it's coax or it's this, but never this. This you only see when you do it in a power cord. Okay? So anyway, keep thinking. So clear, yes?
Those wires will receive the same noise?
You're getting very, yeah, I think that's a correct answer, because what happens is this. If you have two wires and you have a noise source, okay, this is a noise source, the two wires will get different noises because one is a little bit farther, okay? So what it means that if you connect it to an amplifier here, there will be a difference, because typically, even if you're very careful here and do a differential detector, okay, if the two wires don't pick up the same noise, the differential idea doesn't work. So just as this, if you have a wire lying here it may look like they'll pick up the same noise, but if there may be a third wire lying here, and this distance may be double than this distance. Okay? Now if this distance is double, the coupling will be a quarter, because the coupling falls off like at least the inductive coupling falls off like the square of the distance. So if you have two wires and another wire laying next to them, and this is 1 centimeter and this is 2 centimeter, this wire will get a quarter of this wire, so there will be a big difference, and this difference shows up as an error voltage. Okay? Now what happens if you have a twisted wire? For one turn, this wire will pick up a bigger signal. For the next turn, the second wire will pick up a bigger signal. So if you have enough twists, okay, I mean theoretically even number, but it doesn't matter. If you have enough twists, there will be no difference in the voltage between the two wires. Okay? So this is a very simple idea, and it works both ways. It also works for radiation. If you have two wires like this driving an actuator, so these two wires are driving some heavy current into an actuator. If you are sitting here, because one wire is closer than the other, the two currents would not cancel out. Because supposedly current coming in, current coming back, the magnetic field should cancel out. But if there's any distance between the wires, this is closer, so you still get a net signal. But if you twist it at a high pitch, so the average distance is the same of both wires, so the field cancels out. Is that clear? Okay, so rule number one, any connection in that what I'm saying is not just true for servo systems, it's true for any electrical system. If you are concerned with noise, okay, you never use straight wires. You always use this. Okay? There are better ideas if you really have, if the frequency is high and the noise is high. So in a more extreme situation, you use a shielded wire or a coaxial cable. But it doesn't cost anything to twist the wires. So when you do a setup on the table, you have some amplifier, you have some coils, some motors, it doesn't cost you anything to twist the wires, and it already reduces the noise a lot. Okay? Now, remember that whatever doesn't pick up noise also doesn't radiate noise, because it's reciprocal. Right? If something is a good antenna, it's a good receiver for noise, but it's also a good transmitter for noise. So anything, it's exactly one-to-one, because it's the same equation. So basically anything you do to minimize noise pickup, you also minimize radiation of noise. So if you want to be a bit more mathematical about it, okay, if you have a conductor, the conductor creates a magnetic field around it. So you have to analyze two cases. You have to analyze the magnetic field and the electric field, because some coupling can be magnetic, some coupling can be electric. And at very high frequencies, it's the same. We didn't discuss it yet, but you should remember it from electromagnetic theory, that at a very low frequency, you can have a separate magnetic field and a separate electric field. At high frequency, you cannot. Does everybody understand why? You look a bit unsure. Okay. Okay, so that, anyway, I don't have enough time to fully get into electromagnetic theory, but I can show you examples to show that it's correct, okay? If you take a permanent magnet, clearly you have a magnetic field but no electric field, okay? You can hold the magnet, measure the magnetic field, like the Earth has a magnetic field. It's always there's no electric field, okay? On the other hand, if you charge up a piece of plastic by rubbing it on your hair like a comb, obviously it has an electric field because it can pick up little dust, but clearly there's no magnetic field because there's no current flowing. Magnetic field can only come if there's current flowing. Okay? But if the frequency is high, you cannot have one without the other, and the reason is Maxwell's equations. Now, does everyone remember Maxwell's equations? Good. Okay, so let's start from Maxwell's equations. Okay, so Maxwell's equations say that at any point there is an induced voltage which is equal to the derivative of the magnetic field. Okay? And at the same time, so if there is a changing magnetic field, so there will be an induced voltage V, which I'm writing it in the derivative form, not in the vector calculus form, which is just simpler. So there is V is going to be d phi to dt, where phi is a total magnetic field, phi is B times A, okay? And this will be the induced voltage, but Maxwell's equations also said that the opposite is true. If you have a changing electric field, you have to have a current, because everything has some capacitance. So if everything has some capacitance, and if you have a changing electric field, if there is a changing voltage across a capacitor, you'll get a current, and the current will be dc, the capacitance dV to dt. Okay? Okay, actually the current is dq to dt, right? Actually the equation is current is dq to dt, but q is c delta v. So it's the same, okay? So if there is a changing voltage, you have to get a current. Now if you have a current, and the current will be also changing because that's AC. If you have a changing current, you will get a changing phi, and so basically the two are linked. If the magnetic field is changing, you get a voltage. Okay, if the voltage is changing, you'll get a capacitive current, but the capacitive current, like any current, will create a magnetic field. Okay? And if you want to know what will be the magnetic field the current will create, so this is a current I. So we go to the third Maxwell's equation, which says that the integral in a closed loop HdL equals I. Do you still remember this stuff? Good. Okay. Now, H. Okay. So H. So if you remember, mu H is B. Okay. That's the definition of B and H. Mu is the same as we discussed before. Mu is actually mu 0 times mu R. Okay. So we can take the third equation and rewrite it. That's a closed loop integral, and all what this means that if this is I, I'm doing an integration around this path, all around the conductor. So this path is integral dl. Okay, I'm integrating along a closed path as integral dl, So the integral of, so instead of h, I'm writing b over mu. In the Maxwell's equation is written as h, but I'm just rewriting b over mu because we are usually interested in b. dl equals I, okay? So that's the relationship between the current and the magnetic field. So if you have a changing current, because you have a changing voltage, you also have a changing magnetic field, okay? So this is actually useful because if you have a conductor and we want to know the magnetic field at a distance r, the integral h dl is simply 2 pi r, because just if you take out the b over mu, okay, so I wouldn't dwell too much on it, but simply you can imagine if this is a conductor, at all the points around it which are equally distant will be the same because of symmetry. So if I'm looking at an end view, this is a conductor and these are the lines of constant b because they're the same distance. So I can take b over mu, which are constant outside the integral, so I can do b over mu integral dl equals I, and then the integral dl is simply 2 pi r, because now I don't have anything here, except I'm just integrating dl, so I'm getting a b over mu times 2 pi r equals I, and from that I'm getting b equals mu I divided by 2 pi r. So that's a useful equation to remember, and also easy to derive if you don't remember. So what it means that if you're going away from a conductor, the field will drop as 1 over r, okay? But this is from an infinitely long conductor. In real life, if the conductor is short or there is a coil, it will fall much faster. And again, I wouldn't get into the equations, but if it was an infinite conductor, which explains we are assuming this is like a long cylinder of equal magnetic field, it will fall like this. And the important thing to remember that if there is a changing flux, there will be a voltage. If there is a changing voltage, there will be a changing flux. Because changing voltage makes a current, current makes a flux. Okay? So I wouldn't resort to math anymore. This was just to show you how it's rigorously driven, but it's more important to understand it intuitively. So intuitively, when you have very low frequency, dV to dt and dφ to dt are so low that basically there is very little coupling. But once the frequency gets higher and higher, one generates the other, okay? And basically you cannot have a changing electric field without a magnetic field and vice versa. Okay, so now you can see, so now let's go back to this. If you take two conductors and twist them, and one has a current going this way, one has a current going this way, the average distance r is going to be the same. And if the average distance is going to be r is the same, the field here will be 0. The magnetic field will be 0, because one generates minus b and one generates plus b, will be 0. If you don't twist them, one distance will be r, one will be delta r, and then you'll have a field. So that's true for picking up signal, true for radiating signal. Okay, so then the next step to twisted pair, so people thought of that, and originally that's how things were done. But then people thought of it and said, there is a better idea. Why don't we put one conductor into the other? Because if we take one conductor like this, and the other conductor around it, now this current, let's say, is flowing in, and this current is flowing out, but if you have a tube, a conductor in form of a pipe, and you are a distance r away, it appears as if all the current is in the middle of the pipe, because some is a bit closer, some is a bit farther, so it appears like the average current is in the middle of the pipe. So basically it appears that the current going in and the current going out are overlapping exactly, and because they're overlapping, they cancel out perfectly. Okay? Now if you want a proof why, if you have a pipe at a distance r, it appears that the current is sitting in the middle of the pipe, it's a bit like center of gravity, right? But if you want I can show you a rigorous proof or an intuitive proof. An intuitive proof is saying, let's look at 4 points here. These 2 points are at a distance r. Okay, this point is r minus r. The distance here to this point is r minus r. And the distance to this point is r plus r. Okay? So the field contribution of this part, since we know the formula that the field is proportional to 1 over r. Okay? So the field contributions of this part and of this part of the pipe, one will be 1 over r minus r plus 1 over r plus r. And you know the approximation that when r is very small compared to r, so 1 over r minus r, you can convert it to, you can convert this to 1 plus, okay, there's different ways to do this, but let's say the easiest way to do that is multiply, let's see how to, well, you can just add them together, maybe that's the simplest, without the approximation. So if I add them together, I get r squared minus r squared, okay? And on top, I get r plus r minus r. Okay, that's just simply adding them without any approximation, okay? Now, the r cancels out, and r squared is negligible because r is already much smaller than r, so when you square it, it's negligible, okay? So now you get 2r. So basically what it means that if you have a circle, okay, it appears as if it's coming from the center, because these two things, the deltas cancel out, and these two things are already at the center. Anyway, it's just intuitive, it's not a rigorous proof, but you can get a feel for it that if you would integrate, to do it rigorously, you take delta theta and you integrate in a circle, and then you get the same result. Okay? So, but intuitively you can see that if you have a pipe carrying current on the skin and you are far away, it will appear as if the current was sitting here. So if you put inside that pipe a conductor with a current going in the opposite direction, the field will be 0. Okay? So that's very good. That doesn't transmit, doesn't pick up noise. Okay? And that's called a shielded wire. Now physically the pipe, to make the wire flexible, is made from a braid. It's not a rigid pipe, it's called a braid. And a braid is, if you look at the wire I passed around, it's just the braid is just a mesh of wires which act as a pipe. Okay? So all this was known up to here. All this was known until the year. Actually, it's a very specific year where this whole thing, the problems became understood. So the specific year where people realized all this is not enough was 1858. In 1858 something very interesting happened. The first transatlantic telegraph cable was laid between Europe and the US. Okay, that was a historic thing. It was equivalent to the internet today. Because before that cable, it was very difficult to do business between Europe and the US, because you can send a letter on a boat. Okay, and there were already steamships at that time, so you can send a letter on a steamship. It took 2 weeks to arrive, then 2 weeks to come back. So the pace of things was you couldn't get an answer to any question less than a month. Okay, then suddenly a cable was laid, you can get an answer to a question in an hour. So obviously it was significantly changed the world. So in 1858 the cable was laid, and the cable looked like this for different reasons. It mainly looked like this for protection reasons, because it had a conductor, it had an outer layer which had steel conductors. Okay, they didn't so much think about shielding in those days, but then the cable didn't work. The cable was tested on the ground before it was spliced across the ocean. It worked, then it was laid through the ocean, then it didn't work. And then, it was a huge investment. It took, in today's money, like 100, 200 million bucks to lay this cable, and people invested, and everything. The cable didn't work. At the beginning it worked a little bit, very slowly, and then stopped working. And then all the great minds of the time were thinking, why didn't the cable work? Because at the time the best known scientist was Lord Kelvin. So he was pulled into it, and everybody was pulled into it, and they had all kinds of theories, but they didn't understand why the cable didn't work. Especially that it worked on the Earth, because before it was laid in the ocean, it was tested. And the only guy who understood why the cable didn't work and what you should do to make it work was a fellow who was completely self-taught by the name of Oliver Heaviside. And I think I mentioned him before very briefly. He was one of the smartest people alive, but didn't get any recognition. Okay, at least not in his lifetime. Okay, so there's a very good biography of his called Sage in Solitude. It's highly recommended reading, because the guy who wrote the biography was an electrical engineer, so he really understood what Heaviside did. So Heaviside said that A, the cable wouldn't work, and B, if you want it to work, what you have to do, you have to add inductance to it. So Heaviside said, if this represents a cable, the cable was constructed like this, coaxially, but let's say it represents a wire. Heaviside said it will never work, and if you want to make it work, you have to put in coils in the cable. Like every few kilometers you have to put a coil, and then it will work. Okay? And that looked so counterintuitive, because people try to minimize capacitance and minimize inductance, because people knew that the best cable is a wire with zero resistance. Capacitance is bad because capacitance shorts out the cable at high frequencies. So it's very clear why capacitance is bad. Now inductance is bad because at higher frequencies it presents a high impedance. So everybody, even in those days, people knew if this is L, it will present an impedance J omega L or 2 pi FL, which goes up with F. But anyway, so he was totally disregarded, but at the end, in desperation, people started listening to him, and at the end, this became one of the most important inventions in history of telecom, that in order to make long cables work, you have to add coils to them. Okay, now is there somebody here who knows why? Okay, so this has to do with a concept called characteristic impedance. Okay, so when you look at a coax, and if you look at a shielded wire, there's nothing special about it. It just looks like this, like an audio wire. But if you look at a coax, it says on it typically 50 ohm or 75 ohm. Okay? You notice that if you look at any coax, it's printed on it 50 ohm, or sometimes a code, and you can look it up. Like this is called RG174, but it also says on it 50 ohm. You look in your lab, every coax, it will say RG something and then how many ohms. What does this ohm mean? If you have a coax, it says on it 50 ohm. What does it mean? If you take an ohm meter and measure it, does it read 50 ohm? So what does an ohm meter read? If I took this coax and took an ohm meter and measured from the inner wire to the outside wire, what will the ohm meter read? Just imagine, if I took this piece of wire, took an ohm meter, what did it read?
Open circuit.
Pardon?
Open circuit.
Open circuit, of course, because it's insulated, right? Obviously an ohm meter will read infinity. And if I measure one end of the conductor to the other, it will read 0 or near 0. So why does it say on it 50 ohm? So it never bothered you, like when you saw the cables in the lab. It never bothered you why it said on it 50 ohm? Obviously you're not the curious types, but but it should have bothered you, right? Because you used these cables for 6 years or 5 years. Yes?
Is it to match frequencies?
Getting warmer, but not quite. Not quite, because the 50 ohm is not frequency dependent. So anyway, that's a very interesting story. That's why I started the lecture today saying that the least understood part of systems by students is the wiring. Because I've never seen a student who understands what the wiring does and which wiring to use. Okay, so let me get back to the 50 ohm in a minute, because it's very important stuff. Remember, because of misunderstanding of wiring, this first transatlantic cable failed. Okay, so the damage of not understanding wiring was enormous. Okay? So I'll get back to this issue of coax in a minute, but I want to finish the discussion of twisting pairs. So I think everybody understood why you should twist the pairs, but now let me ask you a question. If you have a cable like this, which have multiple twisted pairs inside, okay? So just to finish the twisting of the pairs, what should I do inside this cable? Should I twist all the pairs the same pitch or different pitches? So let's say you have to lay in one cable signals from a few sensors, okay? So inside, so this is a big cable, okay? And inside you have one twisted pair, and if you open any electrical cable, you see that all the pairs are twisted. Every cable in the world is always twisted for the reasons we said. But if you have another pair, should you twist it at a different pitch, or should you twist it at the same pitch? What's best? Pardon?
Different pitch.
And why?
That way they're not possibly being in phase with each other. So
Very good answer, because if you have a twisted pair and you happen to lay a second twisted pair parallel to it with the same pitch, the twisting doesn't work, because these two are always parallel and these two are always parallel, so you don't get this cancellation effect. Okay? Now, should this pitch be some kind of a integer multiple of this pitch or just a random number? Okay, yeah, there is, okay, turns out actually there is an optimal pitch. If you have a whole bunch of wires in a cable, like in a telephone cable, there's maybe 100 pairs, there is an optimum ratio between the pitches, and that's called the Walsh functions. Do you know what Walsh functions are in mathematics? Okay, we skip that. Okay, but anyway, different pitch. The answer is different pitches. Okay, good. So now we ended up with it. Now, last question. Okay, if there was no electrical issue, if this cable was purely for DC, would there still be advantage of twisting the wires? If it was just a cable connecting your battery to some chargers, pure DC, is there any advantage of twisting the cables? Now you have to think outside the box a bit. Imagine a big power cable like connecting your kitchen range, or massive currents, no worry about high frequency or noise. But if you open this cable, it's still twisted. So when you buy a power cable to put in the wall, they're all twisted, the big cables, although nobody is concerned about noise. So why are the big power cables twisted? Well, maybe to radiate, not to radiate noise. But there's another reason, totally nothing to do with electricity, why cables have to be twisted inside.
So, if they heat up, they heat uniformly?
That is true, yeah, it spreads the heat. But that's a secondary, that's a good reason, but that's not the main reason, yes. Of course, flexibility, because if you don't twist the cable, it's not flexible. Because when you bend the cable, see, when you have a cable, when you bend it, the outside wires have to stretch more than the inside wires. Okay, so a cable will be quite stiff if it's not twisted. Now, if it's twisted inside, each wire stretches a bit and compresses a bit, stretches a bit, compresses a bit, so each wire stays the same length. It's the same reason why steel cables are twisted in such a complicated way. You have substrand twisting and twist. If you look at a big steel cable, there is groups, and each group is twisted, and the groups are twisted together. And this is for flexibility. So there's a mechanical reason why all cables have to be twisted, but this is not what we're talking about here. We're talking about the electrical reasons. Okay, so I think we finished with the twisting and pairing. So the short answer is, in a big cable, like a telephone cable, each pair is twisted at a different pitch, and actually there is some mathematical relationship between the pitches, and then you take groups and twist them, and then you take the whole thing and twist it like this with the whole cable for mechanical flexibility. So there's like multiple pitches inside the cable, some for mechanical flexibility, most of it for minimizing crosstalk. Okay, clear? So now let's go back to the story of Heaviside, and why do you have to have inductor? Why did they have to add inductors in order to make the cable work? And this is one of the most fascinating things actually in electrical engineering. Okay, so Heaviside is the first person in the world who understood electromagnetic waves. I mean, there were Maxwell's equation, but the people didn't really understand well this whole issue how electromagnetic waves propagate. And Heaviside is the first person who understood that the way the signal travels in a cable, it's actually an electromagnetic wave. Okay? And because of that, the cable shouldn't be just treated as a resistor or capacitor. It should be treated in a broader way, because an electromagnetic wave, when it travels through a medium, like through the air or through water or anything, it sees something called a characteristic impedance. And you probably learned it in fields somewhere, that there is a characteristic impedance, which is basically the ratio. If you look at the voltage and the current of the wave and divide them, you get a number. And that number is called the characteristic impedance. And that is characteristic to the medium. Okay? So as I mentioned before from Maxwell's equations, the voltage and the current are always linked. Okay? So if you have because one is the derivative of the other and so on, so they are linked. So if you measure them, the ratio is fixed. So that is called the characteristic impedance, and Heaviside is the first one who understood that the characteristic impedance also applies to cable. A cable is just a continuation, the way the wave propagates in the air, like a radio wave propagates in the air. An electric wave that propagates in a cable behaves the same way. So it's not like a DC current from a battery that you make to make change faster. But he also understood that the reason why this was never noticed before, because at the frequencies people used at those days, maybe 10 hertz, 100 hertz, remember that was telegraph, it was before telephone, the wavelengths were so long that you never could notice that things behave like waves. Because if you look at telegraph, which at those days actually they tried to signal at 1 hertz across the ocean. So 1 hertz, the wavelength is 300,000 kilometers. So nothing people tested was even a small fraction of a wavelength. So you never notice that things actually behave like waves the way they propagate. But the telegraph cable was the first time that such a long wire was used. And that wire was, I don't know, let's say 5,000 kilometers, okay? It's still a very small portion of a wavelength, but it's already you start seeing the effect of waves. Okay? So it doesn't behave like, in other words, if you have a wave, one example is if you have a piece of metal, the length of a wave, you can have in the middle a high voltage, and at the ends you can have a low voltage, because you can have a standing wave. Okay? Like in a violin string, you can have the ends not moving, the middle moving. You can have the same in an electric field in a standing wave. So anyway, these things you only see them when the physical object starts getting close to the wavelengths. If you look at a very little piece like this, you don't see that. It seems that it's either signals at the same level. So to cut the story short, Heaviside realized that all the cables should be treated as what's called today waveguides. Okay, and they should be treated that they have a characteristic impedance, that if an electrical signal propagates through them, because of Maxwell's equations, because a current will induce a voltage, the voltage will induce a current, there will be a characteristic impedance inside that cable. And this is given by dividing the momentary voltage by the momentary current, right? So the Z will be dividing the momentary voltage by the momentary current, and this number will be constant and be fixed for a given cable. If you change the structure of the cable, it will be different, because the capacitance will be different per unit length, the inductance will be different per unit length. So when you take the derivatives, the ratio will be different. Now, if you have a cable which is mismatched, so let's say you have something which Heaviside claimed has a unique characteristic impedance, which is defined like that, and you connect it to something else, like a coil or something, you will get a problem with the connection if the impedance is not matched. The best analogy is like change of a refractive index when you have light. When the light goes from one refractive index to the other, then you get a reflection. The refractive index is exactly the same thing, right? It's a velocity of light in the medium. So So he realized that the reason the cable didn't work, because it was treated as a simple resistor, capacitor, inductor, while the cable was long enough that you have already to treat it in a model of wave propagation, and you have to find out its characteristic impedance, and you have to make sure it's matched. And if you looked at the cable of those days, if you looked at the ratio, it was heavily mismatched to the receiving end, which was a coil, say a coil of a galvanometer, and it was mismatched to the sending end, because at one end of the cable there was a switch. So say if this was a few thousand kilometers transatlantic cable, at this end there was a switch and a battery where you send the codes, and at this end there was a high Z galvanometer, because it wasn't sensitive enough for a relay. Okay, so it was completely mismatched. It was driven from impedance 0, it was terminated with high impedance, it itself had some strange impedance, and the whole thing was mismatched. Okay, and so Heaviside was the first person who understood that if you take a cable and you drive it and terminate it with its characteristic impedance, and the characteristic impedance is the intrinsic ratio of V to I inside the cable, then it will be frequency independent, because the characteristic impedance is, if you work it out, it turns out to be a purely resistive. Well, what impedance means basically resistance, right? So if the cable behaves, if you match it correctly, it will behave as a pure resistor of this impedance, and if you match it with this resistance and drive it from this resistance, the whole electrical model of the cable will become like this. This is ZO, the cable. You terminate it by ZO, and then you drive it from ZO, and then it becomes frequency independent because it's purely resistive. So I realize I'm jumping many steps here because it's beyond the scope of the course, but you really highly recommended to read this book about Heaviside. So he said if you try to calculate the actual impedance of the cable, it turned out that the impedance of the cable was way too low to be connected to the receiving equipment. And he said what you have to do, you have to increase the impedance of the cable. Okay? And the way you do that is you put some inductors inside, and the inductors bring up artificially the impedance of the cable so you can match it to the galvanometers which they needed to receive the signal. Another way of explaining it, the signal was very weak, so the coil to receive it had to have many turns of fine wire to be sensitive to low currents. And that was a galvanometer. But if you make a coil with many turns of fine wire, it ends up at high impedance. Okay? So there was no way to match it properly unless you increase the impedance of the cable. Okay? Because the natural impedance of the cable came out as a very unreasonably low number. So I'll show you briefly, I'm just trying to plan my time. Okay, so I'll just show you briefly Heaviside, how Heaviside figured out what should be the correct impedance. Okay, what Heaviside said, if let's say there is such a thing as characteristic impedance. I mean, he assumed there is such a thing, there was no proof. But he said, let's say there is such a thing. So what it means that if a cable is infinitely long and you look into it meaning you will see the impedance between the center conductor and the sheath. If you look into the cable, you will see Z0. Okay? Now, the cable itself is made, the cable itself, a simplified model is you have a bunch of inductors in series and a bunch of capacitors in parallel, and that's a simple model for the cable. The inductance came from the fact that the wire creates a magnetic field which has inductance, okay? Between the middle core and the outside core there is a space with a magnetic field, so it has to have inductance. Capacitance comes from the fact that there is capacitance between the inner conductor and the shell. It's not a parallel plate, it's a round plate, but it's still a capacitor. So the cable can be modeled as distributed L and distributed C. And this modeling is still used today, right? It's called a distributed parameter model. You say per meter, you have this much L, this much C. That's exactly the same today. So he said if you look inside the cable, what you see this model, but it goes on forever. Now, because if it goes on forever, if you cut off a piece of the cable or add a piece of the cable, it makes no difference. Because this is once the cable is long enough, it starts behaving like this model, and if you add to it at the other end another piece of cable, the characteristic impedance will not change. Okay? So his proof, he said, let's add to it a very small section. Okay? So the very small section will have delta L. Let me just clean the board. So he said we have a long cable looking like this, and because this is a characteristic impedance, it doesn't depend on the length of the cable. That's one of the definitions. So we'll add a very small section, maybe a millimeter, and it will have delta L and delta C. Okay? So what we know that the characteristic impedance should stay the same. Okay? So now we know that Z0 equals this section in parallel to the old cable. So now we redraw it, it looks like this. We know that Z0, if we take a section delta L and a section delta C, and we connect to it the old cable, which was Z0, we know it should stay Z0. Because the cable is infinite with Z0, so if we add a little bit of the same, it should stay Z0. Can't argue with that, because if we say it's an infinite cable, why does it matter if we add a little section? Okay? So now we can write an equation. So this is, the impedance of Z is J omega L. That's the impedance of Z. This is 1 over J omega C. So now we can say Z0 equals J omega L plus, now we have these two in parallel. You have Z0 and 1 over J omega C in parallel. Okay? Because this is in series and these two are in parallel. So if these two are in parallel, it will be Z0 times 1 or minus 1 time over J omega C divided by Z0 plus 1 over J omega C. Okay? So anyway, so I wouldn't go through the whole proof because it's beyond the scope of the course, but this is so you open up the equation. This is delta L and delta C, because we're only interested in the deltas that we added. So please change this to delta L and delta C. Okay, so what you do is you rearrange the equation, and then you say the same way we added delta L and delta C, now we can remove it. Okay? And if you do all this, if you rearrange the equation and then set delta L and delta C to be 0, you get a very surprising result. You get a surprising result that Z0 equals square root of L over C. And that is called the characteristic impedance of a cable. Okay? So basically what happens, omega cancels out. And you can do the math at home and convince yourself that if you do that and then set at the end, at the limit when delta L equals 0, delta L is the length. This is delta L, the additional length. So basically when delta L, capital L, and delta C equals 0, the omega term will cancel out. And you'll get this, and now you can see that if you want to raise the impedance, you should raise the L. Okay? So anyway, I'm skipping a lot of steps, but the bottom line is, for every given cable, there is a number that is purely resistive. It doesn't have omega. And if you take this cable and you match it to this number, the whole network becomes a purely resistive network, and it's frequency independent. And that is a breakthrough. Because if I take a normal shielded wire, or any kind of wire, because of the distributed L and the distributed C, when I look at the output. I have a normal wire and I'm driving it at one end looking at the output. This will be amplitude, this will be frequency. Any normal wire will behave like this, because it's really like a RLC circuit, because the wire also has R, okay? So if I do that, maybe it'll resonate a bit, but it will be in general behave like. So basically, a long normal wire with a load, the output at the other end will drop with frequency, because the capacitance will short out. The capacitance here will short out more and more of the signal as the frequency gets higher. But if I take the same wire, figure out the characteristic impedance, load it with that impedance and drive it with that impedance, okay? Then I'll get something like this. Well, at some point it will go down, because everything has to go down at some point. It's very high frequency. But for hundreds of megahertz, it will be flat. Okay? So that was the big discovery of Heaviside. And actually, you have to drive it from Z0. So if you had a battery and you drove it from Z0, you lose half the voltage. Right? Because the way I explained it, you have this cable which has a characteristic impedance Z0. You have to terminate it with Z0. Okay, so you get a voltage divider, Z0 and Z0. So you actually get half the voltage. Even if your source, even if you measure from here, this is another Z0 and your source. But if you measure at the input of the cable and at the output of the cable, since the cable behaves at Z0 and the load is Z0, you get a voltage divider. So the actual signal is half. But it goes like, it stays flat forever. So that is a downside. For example, if you go in your lab and there is a pulse generator or a signal generator, usually on the connector it said Z equals 50 ohm. Just pay attention to it next time. You'll see on the equipment in your lab, especially on signal generators, it said the Z0. You have this equipment has BNC connectors, and usually it says here Z 50 ohm. Even on a scope, it gives you a choice of 1 megohm or 50 ohm on some scopes. So if you try that, you measure this voltage with a scope, you see, let's say, 1 volt. When you terminate it with 50 ohm, it'll go down to half a volt. Because it means that inside, it's 50 ohm, so when you put 50 ohm, you get a voltage divider. So the downside of this system is that you are, in effect, driving a 50 ohm load with a 50 ohm equivalent resistor, so you only get half. But what the benefit is that it stays frequency independent. Okay, so is this part clear to everybody? Okay, so I tell you what has to be clear. You don't have to remember any of that, of Heaviside proof and all these clever ideas. All what you do have to remember that every conductor, every cable has a characteristic impedance, and if you drive it and match it with a characteristic impedance, it becomes frequency independent, and you get a constant amplitude at all frequencies. And that part you have to remember. Yes?
So you'd want to use a higher characteristic impedance for higher frequencies?
No.
Or lower?
No, it depends on your type of load. If your type of load is, say, galvanometer, which by nature is a high impedance, you would have to use a cable which has a high impedance to be matched to your load. So in the case of the transatlantic cable, they had to add inductors to raise the impedance. Same for telephone cables. But if you want to use a load where the characteristic impedance is naturally low, then you can use a cable. So the characteristic impedance of the cable has nothing to do with the frequency, because it will be frequency independent at any characteristic impedance. So you can make a 10 ohm characteristic impedance, or you can make a 100 ohm characteristic impedance. Both will be frequency independent the same way. So it turns out the reason why 50 ohm and 75 ohm are chosen, if you look at home, like the cable TV, it says on it 75 ohm. Okay, all the cables in your lab, they say 50 ohm. There's also 91 ohm and a couple of other odd numbers. But the most common number for cables is 50 ohm, and the second most common number is 75 ohm, and then there's a few odd numbers. Now the reason why those numbers were chosen, although any number would be chosen, because if you make a cable from normal materials with a normal insulator, that comes out naturally, this number. So in other words, if you make a cable, you use polyethylene insulator, copper conductor, this kind of proportion, because you don't want the conductor to be too thin, otherwise it can't carry current. So if you make a cable by practical considerations, say this maybe 1 millimeter, half a millimeter, 1 millimeter here, 3 millimeter here, that's the number you get. So the number was actually derived from what's practical, what's the easiest number to achieve in making cables. But in the case of the transatlantic cable, this number was way too low for what was needed. Also for telephone cables, the number is way too low. So in telephone cables, the characteristic impedance is 600 ohm. So all telephony equipment works at 600 ohm, because that number is much more natural to drive earphones, relays, galvanometers, okay? But in the rest of the world, characteristic impedance is everything is 50 ohm. So next time you go to the lab and pay attention to what it says on the cables and the equipment, you'll understand what it is. Okay, so now you understand the difference between the last two wires. The last two wires look exactly the same. One is called a shielded cable. Okay, the last two, one is a coax, one is a shielded wire. They look exactly the same. If you cut them apart, you can't tell the difference. But one is MECH. The dimensions inside the wire are MECH to give you an exact characteristic impedance, typically 50 ohm. And the other one, the outside wire, is just a shield. A shield meaning it's based on the original thing we discussed today, that if you have a current going in and a current going out, the effects will cancel out. So it will not radiate noise, but it will also not pick up noise. Okay? So when you look at the shielding effect, you can explain it two ways. One way you can explain it is simply it creates a net zero magnetic field. So it also doesn't respond to magnetic fields or electric fields. And the other way to explain the shielding is think of it as a Faraday cage. If you ground the outside wire, the inside wire sits in a Faraday cage. Is there anybody who doesn't know what a Faraday cage is? Faraday cage is basically a metal box. Okay? So inside a metal box there could be no electric field. But, big catch here, all these statements that inside a Faraday cage there's no electric field, this is only true for low frequency or zero frequency. The moment you have a high frequency, everything you learned at school about Faraday cage shielding is incorrect. So basically, if you take something in a metal box, it doesn't mean there is no electric field inside at high frequency. And because you could have all kinds of situations, depending how thick the wall is, depending on many things. So the important message here is that if you treat shielding as just a Faraday cage, that model is very simplistic and it doesn't really work at high frequencies. So just to convince you of that, I'll show you a demo which, at least to me, was quite surprising, because in every textbook it says if you want to shield your equipment, put it inside a closed metal box, because it says inside the closed metal box the electromagnetic signals cannot go in. And you know from experience, when you take your cell phone underground or inside a train, sometimes it doesn't work because it's all metal around you. So if you wrap your cell phone in aluminum foil and you send a message to it, it wouldn't receive it. This you can try at home. So this makes sense. Kind of, you say, I know from experience, if something is inside a metal cage, it doesn't work. Like my cell phone doesn't ring if I put it inside a metal box. Okay? But it turns out it's not true. This is true roughly. But when you look at low-level signals, depending on the construction of that cage, in most cases, if you put something in the metal box, electromagnetic wave will go through and activate it. And to give you a demo, what I did is I made a box from stainless steel, and the box is completely sealed. You can see there's no side which is open. Okay? Now inside this box is a coil connected to an LED. Of course it has a rectifier because the LED needs DC. So there's a coil inside, a rectifier, and an LED. Okay? So by the textbook theory, if there was an electromagnetic field here, or any field, it couldn't penetrate inside the box. Because if there was an electric field, every point on the box will have the same potential. Because it's a conductor, so the potential has to be the same everywhere. So if everything is the same potential, there could be no voltage difference inside the box. That's what's called a Faraday cage. If there is no voltage difference, there couldn't be electric field. There couldn't be magnetic field. But in reality, if I take an electromagnet Okay, and I hold it next to the box and I turn it on. Just a second. You will see to your surprise that the LED, hold on, I'll just place it where I can press the button better. Okay, so this is an AC electromagnet plugged into the power line, and if I hold it next to this box, the LED turns on. Can you see it on? Okay, so this kind of violates everything your textbooks say, right? That inside a shield box you cannot have an electric field. But that's a very important demo, because when you build equipment, you understand now that just because you put it in a box and you grounded the box, it doesn't mean it's shielded. Okay, and we're going to talk a little bit more next week about what do you have to do to have it shielded. But right now I want you to understand that when you deal with lower level signals, just putting it in a box and grounding the box doesn't shield it. If I ground the box, it will make no difference. Okay, for example, I can ground the box. I find something which is grounded, like the computer is grounded, and I can touch some metal screw here. It will make no difference. So it's not because it's not grounded, because it doesn't have to be grounded to act as a Faraday cage, right? Because the theory of the Faraday cage is there could be no voltage difference inside. But the fact is the LED turns on, there is a voltage difference inside. And by the way, that's not a small signal, because the LED needs, the blue LED needs about 3 volts to turn on. So I'm not talking about microvolts, I'm talking that you can generate easily 3 volts inside the shielded box. So that's, and this magnetic field is not that big, because air gap, you know, it acts from a distance. So it's not that I'm looking for a microvolt in a field of 1 Tesla. The field here is 0.01 Tesla, and I'm looking for 3 volts. Okay, so again, even at a distance, it turns on. Okay, so it's actually very surprising. So this will makes you think carefully when you design equipment. Okay, so I know I went through a lot of things a bit fast, so I just so does somebody have any questions about structure of wires and what's the difference between a coax and a regular shielded cable? So if I gave you a piece of wire, if I cut from a cable a piece of wire, could you tell by looking at it if this is a coax, piece of a coax, or piece of a shielded cable? Yes or no? No. There's no way to tell by looking. It's just when it's used at its characteristic impedance, then it's called a coax. But structurally it's the same. And also, it turns out that even things which are not concentric also have a characteristic impedance. For example, if you have just 2 parallel wires, just like this white wire here, this also has a characteristic impedance, because everything I said before about distributed inductance, distributed capacitance is also true for, not just for a coax, it's true for any wire. So this wire, if it also has a characteristic impedance, and if I calculated it, it'll come out to be about 100 ohm or something like this. Okay, let me think. Yeah, it will be about 100 ohm. And in the old days, there was some special parallel wire to connect TV antennas to the TV. It was called twin lead. And this was actually has a characteristic impedance of 300 ohm. So any conductor has a characteristic impedance. So when you use it at that impedance and terminate it properly and drive it properly, then it becomes a transmission line. The general term for these things is transmission line. Now, if you use it just as a wire without paying attention to the impedance, it can be either a wire or a shielded wire. But if you measure its characteristic impedance, which is easy to measure, not with an ohmmeter of course, but if you measure its characteristic impedance and use it at that impedance, then it becomes a transmission line. For example, inside your cell phone, whenever they want to bring the signals in the RF section, they bring it, since it's a printed circuit board, you cannot have coaxes. So the way your signals in your cell phone are brought, there is a PCB, that's a printed circuit board. There is a ground plane, one side is grounded, and the other side has a strip on the PCB. But this dimension and this dimension are very, very carefully calculated, so it will have a characteristic impedance of, say, 50 ohm. Okay, so it's still a transmission line, although it looks like a normal conductor. But the conductor has to have very, very controlled width, the electric constant, everything has to be very controlled, so the Z0 will be constant, so throughout the path of the signal. This only applies to the RF section of your cell phone, right? But even the digital section is also laid out like this with great care. So at high frequencies, you can't just put a wire down, because at high frequencies, the wavelength is very short. So even short pieces of wire, the effect of the wave propagation will be visible. So basically at low frequencies, the wavelength is very long. So if I deal in a normal lab experiment, these pieces of wire will represent a very teeny fraction of the wavelength. You wouldn't see these effects. Reflection, mismatch, transmission line, you wouldn't see that. But if your wavelength becomes this short, like in a cell phone, right? What's the wavelength of a cell phone? If you had to show it with your hands, what's the wavelength of a cell phone? Well, you know roughly. It works roughly at a gigahertz, right? So the wavelength is this long. Another way of knowing is the old cell phone still had an antenna sticking out, and the antenna was about this big. So the antenna is quarter wavelength, if you remember your physics. So this was a quarter wavelength. So wavelength is big. So in a cell phone, everything is close to a wavelength in size. So these effects are very, very big. So everything has to be transmission line. Okay, so I wouldn't start on a new subject, but I'll tell you an interesting story. So when Heaviside discovered all this, he published papers explaining this. Nobody paid attention for many years until they understood he's a genius. And AT&T went to him and said, why don't you patent all this and we'll buy the patent? Because they wanted to have a monopoly on long-distance telecom. And they realized that this idea with the transmission line and adding inductance, that was the key for long-distance communication. And at that time, telephone started already, not just telegraph, and they realized you couldn't make long-distance telephony without these ideas. So they went to Heaviside and says, why don't you patent it and we'll pay you a lot of money? And he said, it's free. I published it. You can use it for free. You don't have to pay me anything. He was a very weird fellow, too, Heaviside. He was a hermit and was a weird fellow. But and they came back and they thought he's playing hard to get. So they came back and said, no, we really mean a lot of money. And he said, no, get lost. And they came back one more time and they said, we're offering you what is in today's money, $50 million. They offered him $50 million for the patent. And he says, look, get lost. I told you already many times. I published it. It's free to use. Everybody can use it. You don't owe me a cent, and I don't want to see you ever again. So anyway, so they were very concerned because then they realized everybody can use it. So they actually did one of the biggest frauds in technology history. They went to another inventor by the name of Michael Pupin. Michael Pupin was quite famous inventor at the time, and they told him, why don't you patent it as if you invented it, and we'll pay you a huge amount and buy the patent. And Pupin had lower ethics than Heaviside, and that's what happened. So Pupin patented it. He basically took Heaviside's work and added some notes and trivia, and patented it as if he invented it. At that time, the patent office and people didn't check carefully. And AT&T bought the patent from Pupin for, again, tens of millions in today's money. And the reason they paid him so much money, because they knew, although they knew it was a fraud, is they said if they paid less, people would be suspicious, that it couldn't be that. Everybody understood this patent is worth a fortune. So they realized if they pay less, people will question the patent. Maybe the patent is weak. But if they paid a fortune and made it public, everybody will believe that's a really very significant patent. So they made Pupin a very rich man, and that coil, that idea, is still today called the Pupin coil, after Pupin, although it was invented by Heaviside. And do you know who Norbert Wiener was? I mentioned him in the first lecture. Norbert Wiener is a fellow who invented modern control theory. Not just PID, but the full modern control theory with all the predictors and everything which is done today in control, basically was invented by Wiener. And Wiener was very bothered by that story. So he wanted to publish it, but he was afraid he would be sued. So he wrote a novel. And let me just remember the name of the novel. Anyway, I'll bring it in next week. But he wrote a novel, a thinly disguised version of this story without naming the names. And he thought that it would be clear to every reader that this novel is about Heaviside pooping and AT&T, but it was not clear to anybody. Okay, and on top of it, the novel was fiction. Basically, was sold as fiction, so it was in bookstores in the fiction section. But the cover jacket of the novel is all full of differential equations. So Wiener thought it would be irresistible to the reader when the cover jacket will be all full of differential equations. But that was one reason why nobody picked up the novel in the book section. So it's called The Tempter. The name of the novel is The Tempter. It's a very hard to get book, but nobody bought it, and the whole story was forgotten. So before Wiener died, he told all his students at MIT about the story because he wanted the story not to be forgotten. Okay, and that's why I know about it, and then I got hold of this novel. But anyway, it's a very interesting story, and it's actually probably the largest fraud, one of the largest frauds in history of technology. Okay, continue next week.